All right, it's 12:30, so let's begin. I think the first, you guys effectively covered two topics for today. Effective values, which is necessary background information to handle complex power. So let's first start with, are there any questions regarding calculating the effective value of a periodic waveform? Anybody got any questions, comments, or concerns about the methodology there? Nobody's saying much of anything. All right, so let's say that I have a voltage waveform T. Where this is time measured in seconds and this voltage is measured in volts. And let's call this 5 volts. And our voltage waveform, let me draw this a little bit better, is a series of rectangular pulses such that our voltage is 5 volts for, so we could say that over one period, we have 5 volts for 0 less than or equal to t less than, 5 volts less than 3 seconds. And then it's 0 volts for the remainder of the period, which would be 3 seconds less than t less than 7 seconds. And it repeats that cyclically over and over and over again. How would I go about finding the effective value of this series of periodic series of rectangular pulses?
Would you take the integral over?
So V effective, there is absolutely something relating to the integral, yeah. So I'm going to put an integration sign here. What do you think the limits of my integration should be? And if you watch the video, you would know what they should be, but this is a periodic function, right? So we're going to integrate over exactly one period. So, well, that's a great question. Is 3 the period of this function? No. What is it? 7, right? So over one period, it's 5 volts for 3 seconds and then 0 volts for the following 4 seconds, and it cycles between those two states over and over and over again. So we're going to measure our period or we could measure our period in a number of different ways. So let me delete this real quick and let's talk about that specifically. So we could say that if we look at the leading edge of our rectangular pulse and measure to the next leading edge, this is exactly 7 seconds. If we look at the trailing edge to the next trailing edge, that is also representative of the period, and that is 7 seconds. We could look at the midpoint of each of the rectangular pulses, and that would also give us 7 seconds. And so all of these would actually be accurate ways that we could perform our integration here, okay? As long as we're doing it over exactly one period, it doesn't really matter where we set our limits of integration. So let's circle back around to our mathematical expression for effective voltage. There is some mention of integration, and we will do it over exactly one period. So we're going to do it from 0 to t. If we want the effective value of the voltage, what are we integrating? Anybody recall?
Integrate the area.
So that's what an integral does, but what mathematical function or whatever is going inside the integral is my question. The voltage squared, okay? So we're not going to be looking at V of t. It's very important that we remember to square the voltage waveform. All right. So this is giving me the area under the curve, or the area under the square of the waveform. The effective value is in some ways representative slightly of the average. So we're also going to have to divide by the period, right? If we have a signal and we want to know its average value over one period, we integrate over one period and then divide by the length of the period to get its average value. The effective value is what's called the root mean squared of a waveform. And so that means we take the square root of the arithmetic mean, which is the same as the average, of the square of the function. So this 1 divided by t multiplied by the integral of the signal squared is the mean of the square. And then we're taking the square root of that whole quantity, which is giving us what's called an RMS value. So in this case, I think we've already decided that our period t is 7 seconds. We've looked at it in a number of different ways and found that. So we're going to have 1 over 7 seconds. And what I'm going to do is I'm going to break this integral up into 2 integrals. And the reason I'm doing that is because we have a piecewise function, right? So this is defined, over one period as 2 different parts, one having a value of 5 volts and the other one having a value of 0 volts. So I'm going to split it into 2 different integrals. So we're going to integrate from 0 to 3 seconds. The value of our voltage is 5 volts. It does not vary with time, so I should not include some time value in there. I got to remember to square it with respect to dt. And then I'm also going to have the integral from 3 seconds to 7 seconds, the second part of our period, where I'll be integrating 0 volts quantity squared with respect to time. Now, the astute among you should recognize that that second integral does absolutely nothing, right? The integral of 0 or the integral of 0 squared over any time duration should be 0. I'm just explicitly showing in this example that I am indeed integrating over exactly one period, even if part of that doesn't count for anything, and it's because the value of the waveform is 0. So let's see, from here, we would have the square root of, let's see, we're still going to have this 1 over 7 seconds. So what is the integral of 5 volts quantity squared? 25 volts squared, units are important, t, evaluated at 3 seconds and 0 seconds. Which would give us 1 over 7. So 25 times 3, yeah, 75 volts squared minus 0 volts squared. So inside of here, we'll just have 75 volts squared times seconds. And our units of seconds cancel seconds. And so finally, we have whatever the square root of 75 over 7 is, units of volts. And we're going to call these specifically volts RMS. This lets us know that we are dealing with the effective value of the waveform versus the instantaneous value of the waveform. So if you ever see something with the units of volts RMS, it means you're using the effective value. So when we talk about the voltage coming out of one of the receptacles around the room, that is not 120 volts DC, nor is it a 120 volt AC amplitude. It is 120 volts RMS, because that is the effective value of the voltage that's being provided by that socket. So do you guys think you could do this series of mathematical steps for any periodic waveform? Right, I mean, as long as you perform the steps in the right order, it really doesn't matter what V of t is. It just needs to be periodic, and then these are the steps you follow. So on your exam, expect at least one question where I ask you to find the effective value of a waveform. And you'll see a couple of homework problems like that, and at least 2 problems on the in-class assignment for today, or the first couple of problems on the in-class assignment today were with regards to finding the effective values of waveforms. So, all right, what are we going to do next? So, did any of you watch the video regarding finding the effective value of a sinusoid? You did. All right. So, if I have V of t is Vm cosine omega t plus some arbitrary phase angle theta v, my effective value is what? I'm not asking for a derivation. You said you watched the video. Tell me what the answer is. Vm over square root of 2. It is that simple. All right. From this, we can define an Rms phasor. So instead of having just a bar over it, I'll do this in a separate line here. And I think I talked about this in the video, but I didn't have a whole heck of a lot of time to review it. So in the time domain, we have V of t. In the frequency domain, we have V with a bar over it, which would be Vm angle theta v. That's how we would represent our signal in the frequency domain. Well, now we're going to be dealing with what's called the Rms Phasor Domain. And so I'm going to define an Rms phasor as, instead of having a bar, I'm going to put that tilde over it to denote that it's an RMS, to denote that it's an RMS value. And so this would simply be Vm over root 2 with an angle of theta v. And this is fundamental to our complex power analysis. So I could also have a time domain current, IT is Im cosine omega t plus theta I. Because it's a sinusoid, the magnitude, what the heck just happened there, of the effective value would simply be Im over root 2. That's true for any sinusoid, regardless of its amplitude, frequency, or phase angle. You always get just the magnitude divided by the square root of 2. And so we can see that in the time domain, if we have I of t, we could convert this to the phasor domain as I is equal to Im angle theta I, and then into the Rms phasor domain as I is Im over root 2 angle theta I. All right. Our complex power definition, S bar, is simply the Rms phasor voltage times the complex conjugate of the Rms phasor current. That is how power engineers have defined complex power. Right? So this would be Vm Im times 1/2, because we would have 1 over the square root of 2 times 1 over the square root of 2 with an angle of theta v minus theta I, or in terms of our effective values, it would be V effective, I effective with an angle of theta v minus theta I. Okay. So this guy is what's called complex power, and it has unit of volt amperes. All right. So this is kind of the representative of the total amount of power that's delivered to a particular load. This quantity, V effective multiplied by I effective, is what's known as the apparent power. It's also measured in volt amperes because it's simply the magnitude of the complex power. How many of you have ever had to buy a universal power supply or something like that for a computer or a generator or anything? I got 2 people raising their hand. So when you buy it, it usually gives you 2 figures of merit, the amount of watts that it can generate and the amount of volt amperes that it can generate. Those volt amperes are the apparent power, right? So it can supply some reactive power if it needed to drive an inductive load like a motor or something like that. But typically speaking, like you might buy a 1.8 kilowatt generator, it might be rated for 2100 VA or something like that. That's telling you effectively how much reactive power you could also supply with it. Let's see, this guy right here, theta V minus theta I is what's known as the power factor angle. We'll talk about that in just a moment. And so this is the 2 different parts of our polar form representation of our complex power have specific names, right? Apparent power and power factor angle. If we put it in rectangular form, using good old Euler's identity, we have V effective, I effective, cosine theta V minus theta I plus J, V effective, I effective, sine theta V minus theta I. Where this whole guy right here is the average power measured in watts. And this whole guy right here is the reactive power measured in VARs, or volt ampere reactives. Okay. Let's talk about symbols here, I guess, real quick. Apparent power is S with no bar over it. Our power factor angle is theta S. Our average power is usually denoted by P, and our reactive power is usually denoted by the letter Q. So these 4 different quantities really summarize all of the information that a power systems engineer would want to or need to know about a particular load, be it a motor or a bank of lights or anything like that. What we're learning here is effectively how buildings like this one, their electrical systems get designed to some fashion. We're looking at these things now as everything is either a source or a load, and these are how they're rated. So let's consider a simple system. Let's say that we have, do I want to do 208. 208, angle 0 degrees, volts, RMS. This would be representative of the voltage coming off of 2 taps of a transformer mounted on a pole outside in a residential neighborhood here in the United States. Particularly, it would be the line-to-line voltage measured, which would be, well, we're not going to get into 3-phase power because that will just piss you guys off. But this is an accurate representation of the voltage that you would see coming off of 2 taps of a transformer. And that load, or excuse me, that source is connected to a home. So let's talk about the types of loads you might see in a home. So you're going to have televisions and things like that, right? Most people own a TV nowadays. Those would typically be classified as a DC or purely real load. Well, I don't want to say DC, so let's say purely real load. And what I mean by that is a television itself is going to have plenty of capacitors and inductors and all that kind of stuff in it, for sure. But nowadays with modern smart TVs and all that kind of stuff that are effectively a small computer inside of your television, all of those turning on the transistors and turning off the transistors is handled using direct current signals. So from the perspective of the transformer, your televisions, LED lights, all that kind of stuff are going to look like simple resistive loads. So let's say that this impedance ZEQ is going to be largely resistive. So let's call it on the order of 75 ohms real part. And there's also going to be some inductive loads. So for every, let's see, if you have a convection oven, which has fans inside of it that blow hot air around the oven, that would be considered an inductive load because it has a motor that's turning the fan blades around to blow air. Your heating, ventilation, and air conditioning system has a couple of motors, so that's going to give you an inductive load. Your washer and dryer likely also would be considered inductive loads, your microwave as well. So we're going to say that in this home, we have 20 ohms of purely inductive loads, representative of all the inductive parts of the motors and stuff like that that are in the home. And connecting the voltage present at the transformer to the loads presented by the house are transmission lines, right? You can look outside and see several of them. And we're going to say that this line has very low losses. So let's call it on the order of 0.3 plus J 0.1 ohms for our losses. So let me ask you guys a question real quick. This is pertaining to this class, but it's not super crazy important that you know this. I'm just wondering how many of you are kind of astute enough to know what's going on. So our transmission line has a real part. What do you think that's representative of? So that is a real part of the impedance. So the impedance, the real part of the impedance is representative of the current. I don't understand. Okay. So how do electrical signals get from, turn around and look out the window over there, okay? So you can see on that pole, there's that big gray doodad right above the tree line, right? That's a transformer. And there are wires running off of that, okay? So how does a signal get from that transformer to, say, that apartment complex over there, or the washateria, if those lines are feeding the left-hand side of the street? Are the signals wirelessly broadcast? How is power delivered? With wires, okay? So those wires are long runs of a crap load of strands of copper. And as we saw on, let's see, this would have been the second or third day of class, whenever we talked about Ohm's law, that wire has a finite resistance, right? Now in our class, we've effectively said that the resistance of wire is so small as to not count. And our transmission lines might be, instead of, a couple of centimeters, tens to hundreds of feet, depending on how far away our home is from the transformer, etc. So they're large enough to where we can no longer just say, well, they're 0, all right? So the real part of this is representative of the resistance of copper over a long distance. The imaginary part of this is because any closed circuit will exhibit some self-inductance, okay? By definition, if you have a section of wire that forms some closed loop, it has inductance. So we are getting into modeling much more real things in this section of the class, okay? So my question to you guys is, how would we go about determining, let's say, the average power absorbed by our home, which is represented by the quantity ZEQ here? Pardon? I'm asking what math we have to do to figure out what the average power, we have an equation for it literally right here, is for our load, ZEQ. I'm sorry, I couldn't hear you. Okay, so the suggestion is that we could determine our current, right? This is a single loop circuit. Does anybody disagree with that? All right. So I'm going to draw our current in blue. Okay. So there's going to be some current, let's call it IS, that's leaving our transformer. That same current is going to flow through our transmission lines to deliver power to the load representative of our home in this case. So if we could solve for the current IS, then we could absolutely, we would know this I effective right here, right? We would know the I effective and we would know theta I. How could we get the other quantities? Or is that enough information? I have VRMS supplied by the source, but that is not the same. So if I want the complex power, all right, so let me revisit something really quick then, okay? If we want the complex power over a particular impedance, then we are going to want to know, so I'm about to use L here, not for inductance, but to represent a load, or I'll call it load actually. So we have some RMS current I load, and that should be an RMS guy over here. But we would also need to know the RMS voltage over our load, V load like so. Because if we want it over this particular thing, we need to know potentially both the voltage drop over it and the current flowing through it, just like any other thing. We're just treating this as if all of the loads being drawn by the house are treated as effectively one generic circuit element, okay? But if we want the voltage, or if we want the power delivered to a particular circuit element, we need to know both the voltage drop over that element and the current flowing through that element, or other information about it. So I would argue that your assessment of we could figure out what the current is true. We could do that pretty trivially. Could we figure out what the voltage is? We could do voltage division, okay. Or we could use, once we know the current, we could do Ohm's law. Or I would argue that once we know the voltage or the current, we actually have enough information to solve this thing. So let's talk about the different ways that we can go about this, okay? And practically all of the problems that we work will have different ways to get different parts of it. Hopefully you guys have come to that conclusion by now. So let's tackle figuring out what I load is first. This is one of numerous ways, but I believe the suggestion is that since we have a single loop circuit, we can really just figure out I load using Ohm's law, right? So we have our source voltage, 208 angle 0 degrees volts RMS, and we would divide that by what? Right, the equivalent impedance of everything seen by our transformer here, right? So that's simply the wire impedance in series with the home impedance, which would be 75.3 plus J 20.1 ohms. So let's take a moment and calculate that. I get 2.669 angle negative 14.946 amps RMS. Anybody else get that same number? All righty. So we could also determine the voltage drop over our load, right? And let's use, what was your name, sir, that suggested voltage division? Brandon. Let's use his suggestion. Using voltage division, we'd have 208 angle 0 degrees volts RMS multiplied by, in our denominator would be the total series resistance. So again, that's 75.3 plus J 20.1 ohms. In our numerator, it would just be 75 plus J 20 ohms. And so we'd have 207.158 with an angle of negative 0.014 degrees. Volts RMS. So we now have the effective value for our voltage, its magnitude, the effective value for our current, the phase angle of our voltage, and the phase angle of our current. So we definitely have enough information to calculate our average power, right? So P average is the magnitude of V load times the magnitude of I load, because those are the effective value of the voltage and the effective value of the current respectively, times the cosine of theta V load minus theta I load, which we would get to be 207.158 volts RMS times 2.669 amps RMS times the cosine of negative 0.014 degrees minus negative 14.946 degrees. So let's see, 207.158 times 2.669 times cosine negative 0.014 minus negative 14.946. So I get 534.234 watts. So we've done our first complex power calculation. How did it feel? Difficult, easy, tedious? Pardon? So that's a great answer. It felt like the same stuff that you have been doing, because it really is. It's literally just taking all of that steady state sinusoidal circuit analysis, taking some of that information and then throwing it into a couple of extra equations. Now, my question to you guys is, do you want to have to remember all of these crazy amounts of equations? No. Pain in the butt, right? Absolute pain in the butt. So what I would like you to do now, so this is one way to do it, and there's nothing remotely wrong with it. Keep these guys, let me put a box around them, in mind. Okay. Let's instead calculate the complex power, right? So the complex power absorbed by our load is simply, again, the RMS phasor voltage multiplied by the complex conjugate of the RMS phasor current, which if you stored these things in your calculator, should be fairly trivial for you guys to do. But just to be clear, we will be multiplying, let's look up here, 207.158 with an angle of negative 0.014 degrees volts RMS. And then I'm going to have the conjugate of my current, 2.9. And the angle here is negative 14.946. So what do I do when I take the conjugate operation there? So I'm conjugating this guy. Who remembers how to take the complex conjugate of a polar form number? Incorrect. Adding 90, it would be converting from cosine to sine, which is not what we're doing. Adding 180 is how we get rid of a negative sign, which is also not what we're doing. That is exactly right. So for a rectangular form complex number, that's trivial, right? If we have A plus JB, the conjugate is A minus JB. So let me refresh you guys' memory. Let's go back to page 1 because I did something weird. So we're on the complex number plane, right? We have real parts over here, imaginary parts on the vertical axis. So for a complex number A, that is A units out in the real axis and B units up in the imaginary axis, A conjugate, as Mr. Carrick just suggested, is we change the sign, on the imaginary part. So we'd have A minus JB. So let's see, that looks like roughly 2.5 units. So this would be minus B. So A conjugate would be down here. In polar form, what has happened? Right, we had our angle and now we have negative of our angle in the conjugate. So that's how we take the complex conjugate of a polar form number. Literally just change the sign of the angle, leave everything else alone. So if we had negative 14.946, we have now positive 14.946 degrees. Yeah. And this would be amps, RMS. So somebody do this math and then tell me what answer they get. Five 552.905. All right. Oh, a standard decimal number, 14.932 degrees. And the units of complex power are volt amperes. Okay. All right. Now, it may seem like this is not helpful. First, did anybody else get this answer? Let's start there. All right, got a couple of people raising their hand. Now, convert that from polar form to rectangular form, please. Pressing like 4 buttons on your calculator, pretty much anybody can do it. 534, all right. So 534.234 K 168, if I read that correct. 468, thank you. And this would be in volt amperes. So, if I can, won't let me pull these things up at the same time. So our answer for our average power here, the way we worked it out the first time, is 534.234, and we get that exact same number right here. That's because the average power, by definition, is the real part of the complex power. So if you can do this simple mathematical operation, multiplying V Rms phasor times the conjugate of the I Rms phasor, you can get the average power. You also get the reactive power. You get the apparent power. You have the means by which to calculate the power factor angle. All of that information is embedded in this one simple and single operation. Meaning, if you can convert between polar and rectangular in your calculator, you do not need to remember 4 or 5 different equations. It's just this one and telling your calculator how to format your answer, which in my mind is significantly easier than remembering all of these different ways. Now, let's talk about a couple of different ways that we could have solved this problem. Is everybody okay to this point? All right. So here's where things are going to get maybe a little wonky or whatever. But when we had a simple resistive circuit, or particularly let's just say a single resistor, and we wanted to calculate the power absorbed by that resistor, we obviously had our relationship V times I, but we also had a relationship V squared divided by R, because if we knew the voltage and we knew the resistor value, that was enough information for us to solve for it. Or I squared multiplied by R, where we only needed to know the current itself and the resistor value in order to calculate the power. We can develop those same exact relationships for complex power, and it's not particularly trivial, okay, or difficult, sorry. So what I mean is, we know from Ohm's law that, for instance here, V load is simply I load, the RMS phasor current flowing through the load, multiplied by the impedance of the load itself, right? So if we substitute this guy into our complex power relationship, we would have S load is I load times Z load times conjugate of I load, right? May not be super obvious how that helps, but I'm going to rearrange things a little bit here, all right? So if I have I load conjugate times I load, multiplied by Z load. All I've done is mathematically or algebraically rearrange things. Do any of you guys remember what happens when I multiply a complex number by its complex conjugate? So let's circle back to page 1 of these notes where I'm talking about complex numbers. All right, so if we have A is A plus JB in rectangular form, or A times the angle, A with an angle of theta A in polar form, right? Anybody got any beef with me saying that this rectangular form and this polar form are representing the same information? All right, A conjugate is A minus JB, which is just going to be A times, or A with an angle of negative A, right? So if I multiply A, sorry, that needs a conjugate sign there, A conjugate times A, this is A angle negative A multiplied by A angle positive theta A is just the magnitude of A squared. Works for any and every complex number. So if you multiply a number by its complex conjugate, it's simply the square of the magnitude. So why this is useful is it allows us to write this as simply the magnitude, of I load squared times Z load. That is all the information that we need to get the complex power. So we don't even need the phase angle anymore. Literally just the magnitude is good enough to get us what we want. We can do a similar thing by noting that I load is equal to V load over Z load, right? So that would mean S load is V load times V load over Z load. We conjugate this whole thing, which simply becomes V load conjugate times V load divided by Z load conjugate. And when we conjugate that fraction, we have to conjugate both the numerator and the denominator. And then this is the magnitude of V load quantity squared divided by the conjugate of our impedance. So we again get a relationship where the only information that we need is the magnitude of the voltage, and that's enough for us to calculate the complex power. And then from that, we would know apparent power, reactive power, average power, power factor, etc. All of that information is buried in these pretty simple relationships. If we were so inclined, we could test any of these. So let's go ahead, I guess, and do that real quick. So let's try this guy right here. That would be 2.669 amps RMS squared multiplied by our impedance of 75 plus J20. And we want the rectangular form of that operation. So 2.669 squared times 75 plus 20i. Convert the answer to rectangular, and we get 534.26. All right, so I'm having 267 here. It's just rounding error. Plus J 142.471. So we still get the correct average power. If we go down here, this is going to be, let's see, what's our voltage? 208 point, or 207.158. Volts RMS quantity squared divided by, that does not look right, 75 minus J20 ohms, because I have to do the impedance, or excuse me, the conjugate of the impedance. I still get 534.2 plus J 142.4. This would be volt amperes, just to be clear. So any of these different formulations work. It's just whatever information is easiest for you to find, use that form, right? Let's see, what else do I want to talk about? Okay, so we've talked about the complex power. The real part, again, is the average power. The imaginary part is the reactive power. The magnitude of the complex power is the apparent power. So let's talk about our power factor relationships and how those guys can be used. Okay, so let's do another thing real quick. Power factor. So what the power factor is, it's a quantity that's representative of the effectiveness of electrical transmission in the system. And specifically what that means is it's the ratio of the average power to the apparent power by definition. So power factor is simply P average power divided by S apparent power. And if we go up to our prior relationships, we would find that this is the same as cosine theta V minus theta I, okay? Now this is where our concept of leading and lagging and all that kind of stuff is going to come back to us, okay? So when the quantity theta V minus theta I, which we may also call theta S, the angle of our complex power. So when theta S is, or let's do it this way. When 0 degrees is less than or equal to, or less than, specifically less than, theta S is less than 180 degrees, our power factor is lagging. By definition, this means that our current lags the voltage, which in turn means that we have an inductive load. We saw that in our last lab, right? Whenever we had the voltage drop over the inductor and the current flowing through the inductor, we saw that regardless of what we changed the frequency to and all that kind of noise, the current lagged the voltage by exactly 90 degrees. Well, in a so for a, what would you call it? Non-purely inductive load, we're going to allow that angle to effectively just be positive, and it will still count as lagging, which means it has some inductive contribution. When 0 degrees is greater than theta S is greater than negative 180 degrees, our power factor is leading, which means that our voltage, or a better way to put this so it's not confusing, I guess, would be the current leads the voltage. And there is a handy dandy mnemonic device for remembering these relationships called Eli the Iceman. So how this works, L is representative of inductance. E is electromotive force, which is just a fancy physics word for voltage. And I is current. And in our second relationship, ice, C is representative of capacitance. So Eli tells us that E leads the current, or voltage leads the current because the letter E comes first. So in an inductor, E comes before, in Eli, E comes before I, so the voltage leads the current. In ice, I comes before E, so the current leads the voltage. It's literally that simple. So that's Eli the Iceman. We've talked about what the angle means, all that kind of good stuff. So now let's put some of this stuff into application. Because in a real engineering design scenario, you're not told, oh, the impedance of this motor is 25 plus J3 ohms or anything like that. You're told how much power it draws, whether that be average power or apparent power, and typically the power factor at which the motor operates. So let's say that we have another system. We have our transformer, and let's use an industrial voltage. So 400 angle 0 degrees volts RMS. This is an industrial voltage used here in the United States. And this transformer or voltage source or whatever you want to call it is used to supply power to several industrial loads connected in parallel. And in this particular example, we're ignoring the impedance of the transmission lines. So we can say that the transformer is close by. So let's say that load number 1, load number 2, and load number 3. Let's say that load number 1 draws 75 kilowatts at a power factor of 0.8 lagging. Let's say load number 2 draws 60 kVA at a power factor of 0.92 lagging. And let's say that load number 3 draws 50 kVA at a power factor of 0.90 leading. And we want to know, let's figure out a couple of things. Right? If we know what our loads, how they're going to behave, let's figure out how much current is leaving our source. One reason why we might be interested in this particular quantity is because we might be trying to size the wires that we're running from our transmission line to our loads. So for instance, if I hooked up a microwave to an outlet here in the room, but instead of using the power cord that came with the microwave, I just effectively soldered up some of the jumper wires that we've been using in our experiments and turned the microwave on, what do you think would happen? The wires would melt. And the reason the wires would melt is because they have a limited amount of ampacity, which is a measure of a wire's current carrying capability, okay? So if you exceed the ampacity of a wire, what happens is the insulation melts, and if you exceed it too much, the wire itself starts to melt. Insulation melting is bad enough because that leaves you with potentials for short circuits and stuff like that. The wire itself melting is a good way to start a fire. So we would want to size our conductors such that they can handle the amount of current we expect it to be doing. So figuring out how to solve for this current that's leaving our transmission line is literally a practical application of the stuff that we're learning here. I would also want to find, let's say, the total complex power supplied by the source. And let's see the power factor at which the source operates. Those are three different quantities of interest that we can solve for using our various relationships in this problem. So this is a circuit just like any other that we've worked, but the information is presented to us in a significantly different way than we are used to, right? We don't know anything about the impedance, although we could find it if we wanted to, but we actually don't need to know anything about the impedance of any of our loads either. So what we're going to do is we're going to use, this relationship, and it's going to tell us practically everything we need to know about these loads, or at least everything we need to know to determine the complex power. So for example, let me put a line right here. The complex power absorbed by load number one. Okay? Our definition is the complex conjugate of the voltage, or excuse me, the RMS voltage multiplied by the complex conjugate of the current, where we have no idea how much current is flowing through there, so that doesn't help us. The other things that we developed, so if we knew what the impedance of the load, we could figure it out that way, but we don't know the impedance of the load either. So again, we're just going to have to use those power factor relationships which are actually extraordinarily useful. So the magnitude of the complex power, the apparent power, can be determined by simply taking the average power, which is what we were given, and dividing it by the power factor, right? Let me write those relationships here so we can see them. So if power factor is defined as P over S, then S, our apparent power, must be P divided by the power factor, right? Simple algebraic manipulation. So we now know what the magnitude of our complex power is. How are we going to go about finding the angle? Well, the angle is simply the inverse cosine of the power factor. And anytime that our power factor is lagging, we know that our angle should be positive. And anytime the power factor is leading, we know that our angle should be negative. It's that simple. So for load one, this translates to 75 kilowatts divided by 0.8 with an angle of the inverse cosine of 0.8, which would give me 93.75 with an angle of 36.870 degrees kVA. So we were able to determine the complex power absorbed by that load, never knowing the current or the impedance. Wasn't necessary. Power factor is also a very strong piece of, or a very important piece of information that we could know. Let's look at load two. This is where things might get a little confusing for some of you, because our methodology here, even though it looks like we have extraordinarily similar information, is going to be slightly different. And the reason is because we were told that the load draws 60 kVA. And 60 kVA is representative of the apparent power, not the average power. So how is that going to change our equation that we used for load 1? It says 60 kVA, kilovolt amperes, where the kilovolt ampere, or the volt ampere specifically, is the unit of apparent power. So go up like 2 pages in your notes and tell me what the relationship between apparent power and complex power is. Right. So the apparent power is the magnitude of the complex power. Okay? Can we agree on that statement? So if I'm trying to use this information to get the complex power, what do I need to do to the apparent power that I'm given? This is a little bit of a trick question. Nothing. Absolutely right. Up here, we were given the average power, and we had to divide by the power factor to get the apparent power. If we are given the apparent power, we don't need to do anything to get the apparent power, right? That's a fundamental mistake I see lots and lots of students make over and over and over again, is not understanding the difference between these units and how it influences your approach to these problems. So for this guy, it should literally be S angle inverse cosine of the power factor, and that's it. Because if you're given the apparent power, you don't have to do any work to find it, right? So in this case, that means that we would have 60 with an angle of whatever the inverse cosine of 0.92 is. 23.074 degrees kilovolt amperes. So what are we going to do for load 3? The same thing, only we're going to drop a negative in there, yes. Now the question is, where does that negative go? So I'm going to do S angle inverse cosine power factor, because we were provided with the information that we have the apparent power. It's 50 kVA. We know what the power factor is, but what does that leading bit have to do with any of this? So it's not going to make the power factor negative. Let's look up here at what we have written down. So when the power factor is leading, our angle is somewhere between 0 and negative 180 degrees, which is just a shorthand notation for it's negative, right? If our angle is between 0 and negative 180, it's negative. If our angle is between 0 and positive 180, it's positive. So we put a negative sign right here, and that's the only adaptation we need to make. So anytime we have a lagging power factor, there's a positive sign that's implied here. Anytime we have a leading power factor, we need to change the sign on our angle. And this simply comes from the fact that when we do the inverse cosine function on our calculator, it's always going to give us a positive number. It can't not do it. So we just need to keep that in mind. So in this case, that's going to be 50 with an angle of negative 25.842 degrees kVA. So we have determined the complex power absorbed by our three loads. How can we use that information to determine the complex power supplied by our source, or the, sorry, this should be an RMS current leaving our source, or the power factor at which our source is supplying power? Anybody have any ideas? So how do I use the fact we know what the complex power absorbed by loads 1, 2, and 3 are? How do I use that information to determine any of these three quantities of interest?
Would you add them all together?
Okay, so the question is, if we add all three of these so the complex powers absorbed by our loads together, does that give us the complex power supplied by our source? Anybody have any thoughts? So let's say that I have the following system. Let's be specific here, okay? 10-volt source. This is a 2 ohm resistor. This is a 5 ohm resistor, and this is a 10 ohm resistor. All right. What is the power absorbed by the 2 ohm resistor? $50 watts, right? So it would be 10 volts squared divided by 2 ohms is 100 over 2 is 50 watts. What about the power absorbed by the 5 ohm resistor? All right, so 100 over 5 is 20 ohms. Sorry, 20 watts. And the 10 ohm resistor? 10. So we know that there is a total of 80 watts being absorbed by our three resistors. How much power is our source supplying? Right. Do we need to prove that? Right. Effectively, the question is it obvious that the amount of power supplied by the source is the same as the amount of power absorbed by the loads? What if it wasn't? What would that mean? Where did that energy go, right? Power is a measure of energy per unit time. So if the power going into the system doesn't equal the power coming out of the system, then energy was either created or destroyed. Can that happen? According to physics, no. Strong no, right? So this is a DC version of our exact circuit, right? We have a source that is supplying power to three loads. So the question of if we add the power absorbed by the three sources together, does that represent the power supplied by the, or excuse me, if we add the power absorbed by those three loads together, does that equal the power supplied by the source? Absolutely, okay? So S source will simply be S load 1 plus S load 2 plus S load 3. So calculator back on. I didn't save any of these variables, so I'm having to go through and type everything in real quick because I don't like rounding error. I get 184.541 with an angle of positive 18.308 degrees kilovolt amperes. Did anybody else add those three numbers and get something similar? It might be a little bit off because of rounding, et cetera, but. All right, so we have determined the total complex power supplied by our source. So how could we use that to determine either the current leaving our source or the power factor at which our source is supplying power? So does anybody have any disagreement that the complex power supplied by our source would simply be the voltage drop or the voltage supplied by our source multiplying by the complex conjugate of the current flowing into the negative polarity terminal, because we want supply power here specifically, right? So what do we need to do? We know Vs, we know S source. We just have to do algebra at this point, right? So that would be Is is Vs divided by S source conjugate. All right. So you may be thinking to yourself, well, gosh, shouldn't the conjugate operation be on the other side with the Is? Well, if we conjugate Is conjugate on both sides, the conjugate of the conjugate effectively, so we flipped the sign on the imaginary portion and then we flipped it back. And in flipping it back, we conjugated the other side. So based on our information here, that is going to be, what is the conjugate of 400 angle 0? Yes, the conjugate of angle 0. 0, still 0. Don't need to do anything there. We could call it -0 if it makes you sleep better at night. There's really no reason to change anything. What's the conjugate of our complex power supplied by our source? Magnitude stays the same. What do we do to the angle? Change the sign. So if we had if we had positive 18.308, we're now going to have negative 18.308 degrees. That is correct. That is exactly right. We are taking the conjugate. So right here, we're taking the conjugate of the quantity Vs divided by S source, which is the exact same thing of taking the conjugate of the numerator and the denominator inside the brackets. And performing this operation, notice that we have a kVA here in the bottom. So if we have volts divided by kilovolt amperes, we're going to get our answer would be expressed in, I have that backwards. I did my algebra incorrectly.
Yeah, I was gonna ask.
Yep. Nope, that's on me. So I'm just going to put a -1 power there. This should be S source divided by Vs. Yeah, there we go. All right, so so that's going to give us units of kiloamps. So I just wanted to be clear about that. So that number, I'm just going to make it times 1,000 divided by 400 gives me 461.354 with an angle of 18.308 degrees amps RMS. So this conductor would be carrying 461 amps of current. So we'd need something pretty large to handle that. All right, our last thing, power factor. It's the only thing we don't have solved for, so let's review our definition. It is the average power divided by the apparent power, or it is simply the cosine of whatever angle the complex power has. So we got two different ways to approach it. Will give us the exact same thing. So I'm going to do the lazy route. So our power factor is simply going to be the cosine of 18.308. Which is 0.94938. We don't need that many figures, but whatever. Is this power factor leading or lagging? Why? Exactly right. That is literally all that you need to do. If the angle is positive, it's lagging. If the angle is negative, it's leading. It's that simple. All right. We only have 25 minutes left, so let's take a moment or two to look at some of these web work problems, because there's at least one that can get a little bit hairy. Engineering 221, that's us. So we're looking at homework set 23 now, I believe. Let's look at problem 1 here. It says a voltage source Vs is connected across an 8 ohm resistor. Find the average power absorbed by the resistor if Vs is given as these different functions. So there are a multitude of different ways to approach this problem. However, I would argue that finding the effective value of the voltage waveform is going to be the easiest way to go about this. So the effective value for part A is literally just going to be 3 over the square root of 2 because it's a sinusoid. For part B, Notice that your sinusoids have the same frequency, which means you could convert them both to cosine functions and then add them together, and you would have a single sinusoid of which you could take the effective value of rather trivially, just by dividing that magnitude by the square root of 2. For part C, you have two different sinusoids, and they have different frequencies. And so that's going to make things a little bit tougher.
Dr. Hartman?
25 minutes.
Could you please share your screen to the Zoom?
So let's say that I have something slightly new here real quick. We'll save you guys a lot of time. All right, the first thing I'm going to do is I'm going to introduce a trig identity that I believe Davis should have introduced the other day. And it says that whenever I have cosine of angle 1 multiplied by cosine of angle 2, this is the same as 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. And there's a similar one for sine functions, but I'm going to be lazy and just tell you guys to convert all of your cosine functions to sine functions, and then all of your sine functions to cosine functions, so that we just have to use this one single trig identity and try, instead of trying to remember 4 different ones. So if I have a signal, let's call it f of t, is equal to a1 cosine omega 1t plus theta, let's call it phi 1, so it's not as confusing, plus a2 cosine omega 2t plus phi 2. And I wanted to find the effective value of that thing, I would wind up having to take the integral of the square of that function by definition, right? If I want the effective value of a waveform, I square the waveform, then I take the average value of the square, and then I take the square root of that average value. And by definition, how we get the effective value. Well, if we notice here that when we square these guys, this is going to be a1 cosine omega 1t plus phi 1 plus a2 cosine omega 2t plus phi 2 times that exact same thing. a1 cosine omega 1t plus phi 1 plus a2 cosine omega 2t plus phi 2. So applying our first trig identity, when we multiply this guy times this guy, that's going to be 1/2 of a1 squared times the cosine of theta 1, which is this angle omega t plus phi 1, minus this guy over here, which is also omega 1t plus phi 1. So when I subtract this angle, or when I subtract this angle from this angle, what do I get? What's omega 1t plus phi minus omega 1t plus phi? 0. They cancel each other out, right? So cosine of 0 is just what? Plus 1/2 a1 squared cosine twice omega 1t plus twice v1. That's me multiplying the a1 cosine blah, blah, blah times the a1 cosine blah, 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 and applying that topmost trig identity. When I multiply that first bit by this bit, I'm going to get, let's put it here because this one's going to be larger, 1/2 a1, a2. When I take the difference, it's going to be cosine of omega 1t plus v1 minus omega 2t minus v2. And we could then group the frequency terms together, which I'll probably do in another step in a minute, plus 1/2 a1, a2 cosine omega 1t plus v1 plus omega 2t plus v2. Then I need to do this guy times the first guy. So that's going to be 1/2 a1, a2 cosine omega 2t plus v2 minus omega 1t minus v1 plus 1/2 a1, a2 cosine omega 1t plus v1 plus omega 2t plus v2. And then lastly, when I multiply the a2 bit by the a2 bit, I get plus 1/2 a2 squared plus 1/2 a2 squared cosine twice omega 2t plus twice v2. That's a whole crap ton of math, okay? What I'm going to do now is look at a couple of things, all right? So I have a DC term, so that's going to be 1/2 a1 squared plus 1/2 a2 squared. Then I have this guy right here, which is 1/2 a1, a2 cosine omega 1 minus omega 2 t plus v1 minus v2 plus 1/2 a1, a2 cosine omega 1 plus omega 2t plus v1 plus v2. If we look at this guy right here, it's going to be omega 2 minus omega 1t plus v2 minus v1. So it's the exact same thing as this guy, as this term right here, but with exactly negative of the angle. So let me ask you guys a quick question. What is cosine of negative x equal to? Exactly right. So this term is the exact same thing as this term, except that it has the negative angle. So that means we're going to get rid of that 1/2 right there because it's doubling that same term, okay? So I just want to be clear about what I'm doing. And then this guy right here, so we have a1, a2 cosine omega 1 plus omega 2t plus v1 plus v2. So this guy, hold on, I screwed that up. right, stupid. Sorry. So the bits where we take the difference actually represent the exact same angle. It's just the cosine of negative x and cosine of positive x. And over here, omega 1 t plus phi1 plus omega 2 t plus phi2, it's the exact same angle again. So we're going to get rid of this 1/2 side. And then we got that guy taken care of. And then finally we have this 1/2 a2 squared cosine twice omega t. Sorry, I forgot something here. I'll get to it in a second. A2 squared twice cosine twice omega 2t plus twice phi1. And then the other term I forgot is 1/2 a1 squared cosine twice omega 1t plus twice phi1. So I went from 8 terms to 1, 2, 3, 4, 5, 6 terms. Yeah, okay. This doesn't seem like much of a simplification, all right? But you have to remember what we're going to do to this thing, right? We're going to take the integral of it over exactly 1 period. So what happens to this term when I take the integral over 1 period? So this is cosine omega 3, right? It's the difference of some frequency, which is a frequency itself. So if I have, just for the sake of argument, a cosine function, and I'm going to pretend the phase angle is 0, but it doesn't really matter what the phase angle is. Here's the period. What happens when I take the integral of that? Zero. Why? That is exactly correct. The area above the x-axis and the area below the x-axis exactly cancel each other out when I take the integral of a sinusoidal function over exactly 1 period. So when I take the integral of this guy inside of my RMS equation, and the integral of this guy, and the integral of this guy, and the integral of this guy, they all go to 0. So the RMS value for this big ugly thing, right? So for f of t is equal to a1 cosine omega 1t plus b1 plus a2 cosine omega 2t plus b2. F effective is simply going to be the square root of 1/2 of a1 squared plus 1/2 of a2 squared. But we can get more generic, all right? This is simply square root of, I'm trying to think of how to best put this. F effective omega 1 quantity squared plus F effective omega 2 quantity squared. Meaning, if I get the effective value of the first frequency term and square that, and the effective value of the second frequency term and square that, and then take the square root of that sum, I get the effective value for that multi-frequency thing. And we can generalize that for an infinite number of frequencies. So for example, let's circle back around to that WebWork problem, right? So problem 2, let's just, so part C, my argument is that if I take the square root of 3 divided by the square root of 2, because that is the effective value of this first part, the sine part right there, with a frequency of 200t, and square it, and I add to that 6 over square root of 2 quantity squared. That's being difficult, all right. So 3 divided by root 2 squared plus 6 divided by root 2 squared. 45 over 2, take the square root of that. I get 4.743 blah, blah, blah. I'm gonna feel like a jackass if this doesn't. 4.74. So these are at 2 different frequencies. What did I do wrong? I know this is exactly how it works, so why isn't it working? They're at 2 different frequencies. 3 over the square root of 2. See if this is just WebWork being a jerk. Nope, not WebWork being a jerk. Me doing something stupid. All right. The effective value at our first frequency squared plus the effective value at our second frequency squared Why is this not working? Those are at 2 different frequencies. I know how to do math. Why is it not working? All right, I might have to circle back around to this at the beginning of class on Wednesday, because this is frustrating me, because I know this is exactly how it's supposed to behave. So I can't figure out what very simple mistake that I'm making here is. Those are at 2 different frequencies, yeah. All right, well, like I said, I'll figure this out and then we'll circle back around to it. So I would skip parts C and D of this homework assignment for a minute, and then we'll get back to it. But all the other stuff should be legit. Let's look at, let's look at problem 2 real quick. One thing that I want to point out here on problem 2, in parts D and E, you're asked to calculate the power absorbed by ZL, etc. And it's specifically asking for the complex power, okay? Notice that the voltage that is given here is not in units of volts RMS. So that means you're going to have to convert that to its effective value simply by dividing the magnitude by the square root of 2 before you're able to answer parts D and E. So A and B do not want the RMS values, D and E require the use of RMS values. That is, I'm hoping unintentionally tricky, but I want you to make you aware of it because it's a really easy problem to get super frustrated on because you're doing everything right. You're just not noticing that the problem switches from phasers to RMS phasers for whatever reason smack dab in the middle of it. 3, you're asked for the complex power. Notice again, you are not given an RMS value, so you need to convert. Problem 4, same deal. You're not given an RMS value, so you need to convert before you can do any of that stuff. Problem 5, you're finally given RMS values, and it's easy street. All right. I will catch you guys all on Wednesday. I am now going to frustratingly sit here and figure out why my answer isn't working for problem 1.